Hey there folks, welcome to this video 6 in this Python Pygame series. We're making the game Othello, also known as Reversi. We've already pretty much built out the game. There's just a few final touches that need to be done, and we also need to include the computer player. Now, the computer player is going to be using the MiniMax algorithm. Um, the MiniMax algorithm is an algorithm that's used to create an AI for two-player games for a computer player, where the computer then will select its best move and then play through a search of, basically does a search of various outcomes from all the different moves that are available at each stage of the game. So you set it to say, okay, we want you to look almost like 3 rounds into the future and evaluate the best outcome, and then return back which move will lead to that outcome. That's a very short way to explain it. So we're going to go ahead and implement that little algorithm into this game for the computer player. Once we've got that onto the game, then we just need to include the final finishing touches like adding the score, adding the new game screen, adding the game over screen, and then this video will basically be done. So let's see if we can get it all done in this video. So the first thing we're going to do, so what we're going to do is we're going to come down to the bottom of our program, underneath the token, just above the tokens. Yes, underneath the tokens, we're going to create our computer player. So let's create a class. We're going to call it computer player. We don't need to pass it any arguments, or we will, but we'll do it in the init method. Init, no, come on, init self. And the only thing we're going to pass it is the actual grid object. And we cannot spell this morning. Right, so we're going to go with self.grid is equal to the grid object. Come on, grid. Just readjust the grid object. Alright, and then we're going to create the MiniMax algorithm. It's going to be the computer hard player. So the MiniMax algorithm also uses recursion. So let's go ahead and create this method. We're going to pass it the grid. So the original grid, we're going to pass it the depth. We're going to give it an alpha value. We're going to give it a beta value. And we're going to give which is the current player. Right. So the first thing we want to do in this algorithm is we want to create a copy of the original game grid. And the reason for that is we do actually, the computer actually makes some moves. It makes a move for every available move that's available. It will make a move, and then it moves on to the next round, and it makes a move for every available move, and then it moves on to the next round. It makes a move for every available move for that one. And we don't actually want this to happen in our original grid. We could do that, but then we would have to reverse all of those moves in our recursive function. I think it's a lot easier. We just make a copy of the grid, and then it will just make the next move onto that grid. And each time it moves through the algorithm, each round it moves through, it just creates a new copy of the grid. Okay, once we've done that, we're then going to create a variable called the available moves. We already have this function, so we're just going to, this method created in our grid object. So we're just going to say self.grid dot find available moves. Grid.find available moves. Right, and to do that we need to pass it to the new grid, which we've just created, and the current player. Oh my goodness, and the current player. All right. Now we've generated a list of available moves for the computer player to actually make. The first thing we need to do is we're going to check the depth level. If the depth is equal to 0, right, that means that we've basically reached the end of our search depth. We then want to calculate what is the best move and score. And that's going to be a function that we're going to create in a moment called evaluate board. And we need to go up to the top under our utility utility functions and create that function. So right back at the top, under utility functions, under the load sprite sheet, we're going to create a function called evaluate board, right? And when we evaluate board, we're going to pass it 2 arguments, I think. Yes, we're going to pass it, we need to pass it the grid and the player, right? So basically we're going to have a score variable, which is going to be equal to 0, and then we're going to cycle through our game grid, enumerate grid for x column, and enumerate row, x column and enumerate row. We're going to say the score is minus equals the column value. So basically the computer player is a -1. So that's what we're going, cycling through each of the cells in the grid, and then we're going to return the score. Because if you remember in the last video, when we created the game, there's the game itself. If I right click, there's my computer grid. It's filled with zeros, ones. Right, the -1 is the computer player token, and the positive ones is the player position. Okay. So to calculate the score, every time it picks up what the computer player score is, it's a -1. But because when we're already doing it as negative, it swaps it over to a positive. So each time it counts a -1, it'll count it as +1 to the score. If it counts a regular one, it'll subtract that from the score. So the computer is always looking for a positive score when he's evaluating the board, and not negative. Okay, let's go back down to our class, our method that we're busy building. And in our method, we've just done an evaluate score. Okay. So we've reached. So once we've reached the end of our depth, we must then do a calculation of the board. We must evaluate the position of the board, whether it's favorable or not for the computer player. We're then going to return the best move score. So currently the best move is set to none because we're at the bottom level, and at the bottom level we're not going to know what the best move is. This is just calculating to return back what is the best score, okay, or the best outcome. Then we're going to say, well, if len, also we need to check if the available moves, so basically if there is no more moves available, then we've also basically reached the end of the search algorithm that we can actually look for more moves. So then we need to do the same evaluation, which I'm then going to copy paste that here. Wonder why I didn't do that as move score. I wonder why I didn't just do that together here as an OR. I'm going to do that for now. Okay, let me just comment this out. I'm going to say if depth is equal to 0, or len available moves is equal to 0, right? And then I'm just going to move this out. That should do the same thing, right? We'll just run the algorithm and see if it works correctly. Then we're going to say if player is less than 0, right? So the player score, the player is less than 0, basically to determine if the player is currently the computer player, because computer player is represented as a -1. Then we're going to say the best score is set at -64. So any score that gets calculated right now will be better than the best score. So it will return what is the current score. We're going to say the best move is going to be equal to none currently. All right. And as we go through, we're going to say, okay, well, for move in available moves. So now we're going to cycle through each of the available moves, and we're going to make a move. X, Y will be equal to the move, right? Then we're going to create a variable, swappable tiles, not a variable, a list. Remember the list we created earlier, the swappable tiles. Basically, that's going to say, well, self.grid.swappable tiles, x, y, new grid, and player. So that is basically it's making a move, and it's going to swap over all of the tiles after that move is made. Then we're going to update the actual game grid itself, that individual spot, right? And then for tile in swappable tiles, we need to then update game grid as well. To be equal to the player. Right. So basically what we've done now is we've gone through it for each, we're looping through the available moves list, and then we are then creating, okay, according to that move, what are the swappable tiles? This is a list that's created of all the tiles that are swappable according to that move. Then we update the grid with our player, and then we upgrade all of those tiles in the swappable tiles list according to what the player is. Right. We will then move value to variables. It's going to be equal to self.computer hard. So this is where the recursive function, it's a method, but the recursion takes place. It then moves on to the next level, the next round. And just remember, we're still in this loop. So we're currently looking at the first move in the available moves list. So we're looking at the first move. So say it makes a move on A3. And then according to A3, the grid has now changed. A3 has been played. It will then recreate the entire game grid in the next method. And then generate a whole new list of available moves. And then make a move according to each one of those moves. So that's why they always say, like even in the chess algorithms, like Stockfish and things like that, they all of these algorithms, they talk about it's a search method or a search algorithm. Because basically it's searching for the best outcome out of all the possible moves that can be played. It took me a while to understand that because I could never understand why they were talking about search when they were talking about generating the AI for board games and things like that. I hope this it's a light bulb go off in your head like it did in mine. Right. So what is done now is when we recall this recursive function, it's switching the player over from the computer player to the actual player, and then generating what is the best move for the human player. It's simulating it, right? And then it will then simulate it back to what is the best move for the computer player. And that's how this MiniMax algorithm actually works. So once it's generated through all the way down to a depth of level 0, it will then return items. And what we want to do then is we want to then check to see if that value of the best score, if that value returned from the recursive function is better than our best score. And remember, our best score is currently set to negative 64 in each iteration. In each iteration of the recursive function. Right? So when it returns a score, it should automatically be better than this negative 64. We'll then say, well, the best score is equal to value. The best move will be equal to move. Right? We then set up what is the alpha variable. The alpha variable is actually the max between the alpha and the best score. Yeah? Right. So the alpha variable that we just generated is basically, we're going to be branching through our algorithm at the moment. So instead of having to play through every single branch of every single move, we're doing a score to see, well, if the best score is bigger than the alpha, then we must follow along that path. But if the best score is not bigger than the alpha, then we're not going to follow down that path of the moves. Yeah. It's a very short answer. There's plenty of great videos out there on discussing MiniMax algorithms and the alpha beta trimming. So then if beta is less than or equal to alpha, break. Right, once we've done that, we're going to go down to, then, or actually we're going to go back to, we're going to create a new grid, which is going to be equal to a copy dot deep copy of the grid. Okay. Why do we do that there? Why do we do that? So we made a copy of the new grid here. Oh, okay, obviously. So for move and middle move. So once we've finished doing all the stuff for the first move in this list of available moves, we then need to regenerate the game grid again, because we don't want to have this move that we've just played on the grid still there. So we basically regenerate the grid from its current position. That's why we do this. New grid is equal to copy dot deep copy grid. That's why we do that. And as soon as we learn how to spell, things will go better. All right, so that is the computer player in the computer, the max part of the algorithm. We're now going to do the min part of the algorithm. We're then going to say, well, if the player is greater than 0, which means that it will be the human player, because the human player is assigned the value of 1, we're then going to say best score is equal to 64. Now remember, this time it's going to be generating negative figures. Best move will be equal to none. And then we're basically performing the same functions as we did above for move in avail moves, but with a few changes. X, Y is equal to move, right? Swappable tiles will be equal to self.grid dot swappable tiles method. X, Y, new grid player, right? In the new grid, we're going to make the move for the player. X, Y is equal to player, right? I'm going to say for tile in swappable tiles, new grid 0, no, new grid tile 0, tile 1, right? That'll be equal to player. Then we're going to say for B move value, it's going to be equal to self but computer. Again, the recursive method is being called new grid depth -1 alpha beta player, right? We're then going to check, still within the for loop, we're going to check, well, if the value is less than the best score, right? Best score will be equal to the value. Best move will be equal to the move being made. And then we're going to say, well, beta will be equal to the minimum between the beta value and the best score value, right? And then we're going to check, well, if the beta is less than or equal to the alpha value, we're going to break out of this for loop because we no longer need to carry on down this branch. We're then going to say new grid is equal to copy dot deep copy grid. Then we're going to return the best move, the best score. Right. That is our computer player built. And actually, we could do this a little bit better. You see there's quite a bit of repetition here. This whole section here is the exact same. That best score. So this whole section here is the same as this whole section here. So let's create a little method just to replace it. If what should we call it? What should we call this method? What should we call this method? Search function, or why not? Let's just call it that. I will give it no arguments for now. Then we just need to take these items. They are the exact same, right? Yeah, they are. They're the exact same. Copy it. We're going to paste it there. Okay, we are going to need to pass it a few arguments. So div search function, self.search function, right? We are going to need to pass it the move. We're going to need to pass it the move. We will need to pass it the grid and the player. Okay. New grid, player, and move. Okay, new grid, depth. We need to pass it the depth. We will need to pass it the depth value as well. Depth. No, this is actually going to make it worse because it's no. Let's not do this. You are more than welcome to go ahead and do it. Suddenly adding a bunch of things that I'm not sure about right yet. Well, I'm not comfortable just changing as yet. Okay. But anyway, there's our search algorithm, our MiniMax algorithm. We now actually need to create the computer player in the game itself. To do that, we're going to go to our, where did I do it? Where was it? Was it in the actual Othello game? Yes, it was. So right at the top in our Othello game class, in our init method, we're going to put it here underneath our grid. We're going to say self.computer player is equal to computer player. And remember the argument we have to pass it is the grid, so we're going to give it self.grid. Okay? Right. Now we actually need to create a way for the computer to know when is it the computer's turn to play. When is it the computer's turn? We're already switching over the computer the player, which player it is. So in our self.update method, that's where we're going to actually start doing the stuff for the computer player. So here in our update method, we're going to say if self.current player is equal to -1, right? We're going to first, remember earlier on we created this time attribute, self.time. And in my input method, we've got a self.time gets a Pygame.ticks. The reason for that is for the computer player's turn, so that it doesn't immediately make a turn. It at least has like a second or two to think. So what we're going to do is we're going to create a new variable here called new time. And the new time is going to be equal to Pygame.time.getTicks, right? So after we've made our turn in the input variable, after we've played our turn, our self.time attribute is given a new time, right, by Pygame.time.getTicks. It then switches over to the computer player in the update method. The computer player will then say, well, if it is my turn, I create this variable called the new time. And that new time is given by Pygame.time.ticks as well. And then we're going to say, well, if new time minus self.time is greater than or equal to 1000, basically 1 second, right? We're going to go cell score is equal to self.computer player dot computer hard, because that was the method. So we're calling the method. We need to give it the grid, self dot grid dot grid logic. Right, depth. Well, this is the level we want the computer player to search for this number of moves. So we want the computer player to basically look 5 rounds into the future. Okay. We're going to give it its negative 64 for the alpha, and 64 for the beta, and the negative 1, because that's the computer player currently. Right. Once it's done that, so it's going to run through that recursive MiniMax algorithm. It's going to return for me the cell and the score. So the cell, which cell it wants to actually make a move to, which is the best move for it to play. So we're going to say self.grid.insert token. Token self.grid.grid logic, right? Self.current player, cell 0, which is the x, and cell 1, which is the y on the grid coordinate, right? So it's made its move. We're then also going to calculate what are the swappable tiles, right? Which is a list, self.grid.swappable tiles. And we need to pass it x, which is cell 0, cell y, which is the y, cell 1, which is the y, self.grid.grid logic, which is the grid, and self.current player. Right. So it generates a list of the swappable tiles. And then we're going to go for tile in swap. Hey, my goodness. Tile in swappable tiles list. We're going to go self.grid.animate transitions, the tile, and self.current player, right? And self.grid. So that's where that animate transition, that changes the color of the tokens, but we actually still need to change the actual grid logic, tile 0, tile 1. It's going to minus equals negative 1. So that swaps it from a 1 to a negative 1. All right. Once it's done that, we then need to convert our player turn, or the computer turn, to the player's turn. Self.current player is multiplied by equals negative 1. That will switch, that swaps the player back to the player's turn. Okay. Let's give this a go. Let's see what happens. Okay, so the game's running, so far so good. If I select this tile, the computer should then make a move after 1 second. Oop, we have a crash. On line 348, in computer hard, the method, we have made a spelling mistake. Let's go down to line 348. And in line 348, we do not have a new T-grid. Okay, let's correct that spelling mistake. Let's run the code again. I make that move, and the computer doesn't make a move because the evaluate board is missing 2 required positional arguments, grid and player, in line 308. Yes, guys, I know. There. Oh yeah, evaluate board. We actually need to pass it 2 arguments. Oopsie. Let's go back up to our arguments. Wait, hang on. While we're here. So evaluate board takes 2 arguments. We need to pass it the grid. So new grid and play. That's all we need to pass to it. Was it? Without being silly. That's correct. That's all we need to do. Evaluate board. Where's evaluate board? Grid and play. Oh. Computer hard. Evaluate board. Just primary grid or a community grid, doesn't matter. Alright, let's try run this one more time. That's 2 errors so far. I'll make a move. Computer makes moves. Cell, score, self, computer play, computer hard. Cannot unpack non-entropy, non-type object. Line 100. So when it's calling the computer method, right, so the issue we're sitting with actually is I'm made a mistake here, and I hope maybe you picked it up. I hope you did. So once we've done the max portion of the MiniMax algorithm underneath our new grid line 335, we actually forgot to return the best move, best score. We actually forgot to do a return here, which doesn't help at all. So let's try go and see if the game works. Now, if I make this move, computer makes a move, I make a move, computer makes a move, I make a move, computer makes a move. The computer seems to be making moves, and technically speaking, the computer should beat me. I'm not going to play for too long. I just want to see what he does. Yeah, he seems to be making it very difficult for me. Right. Things seem to be going poorly for me. So maybe this is one of those rounds that I can win. I don't know. Or we'll see. I've basically blocked out. There's no more move. Oh, there's a move for me. And I've lost. There's no moves for me to make. Look at that. Computer wins. All right. The next thing we to do. The interesting to note about this algorithm, right? So one of the most interesting thing to note about the MiniMax algorithm is actually the evaluate board. So if you think about it, that's where you actually calculate what is the winning position, what is the position that the computer is chasing. So at the moment, I've only got it set so that the computer has more tokens on the board than the player. It doesn't calculate. It's not trying to set all the tokens to black. It's just looking to have even one more black token than white token. So it's playing 5 rounds ahead, and it's looking for how to play it to ensure that 5 rounds later, it has more tokens than the player does. That's so if you think about it, the MiniMax algorithm actually comes down to how do you evaluate the board and at what point in the game, which is quite an interesting thing to note. You could then go ahead and play with this evaluate board. You can give values, higher values to certain positions on the board. In one iteration of this game that I gave a higher value or higher weighting to the corners, so that the computer player would always try and chase the corners as well to make sure that it at least own the corners and then also own the edges. Because if you own this edge here, you could basically always switch tiles over any tiles that are played on the rows along that edge. Right, so that's going to be enough for this video. I'm going to call it there. In the next video, we're going to be basically just finishing off the game. So if you've enjoyed this one, if you like this video, if you like this content, please hit the subscribe button, hit the like button, share this video with your friends even if you want to. It really does help. And let me know down in the comments if you're following along and if things are working out for you. If you've got any tips or improvements, that'd be great. I'll see you guys in the next video. Cheers for now.